All right, so welcome everyone. Our speaker is Stefan, who will talk about simplifying transformer blocks. Go ahead, Stefan.
All right. Thanks everyone for coming to the Journal Club. I'm going to talk about this recent paper about simplifying transformer blocks by Bobby He and Thomas Hofmann. So hopefully this is not going to be too long of a Journal Club because the basic changes to transformer block are quite simple, but hopefully it's going to be fun. So yeah, before we dive into this paper, I just wanted to go over the basics of attention mechanism in transformers. So what is the idea of transformers? So the idea is to construct token or word representations that are going to be contextual. So we have sentences like, I'm sitting by the bank of the river versus I'm going to withdraw money from the bank. Then we want the word bank to have different representations in two sentences because its meaning is different. In one of the sentences, we want bank to be close to money in embedding space. In another one, we want bank to be close to river. So the idea of transformers is that, if we start with some sets of token representations, then we can iteratively refine those representations by replacing the representation of token at position I with a weighted average of representations of tokens that came before. So the bulk of the attention mechanism here is going to be about learning the coefficients in this weighted average. So we want to learn, which things are similar to I, and therefore whose coefficients in this weighted average of I should be significantly non-zero. So schematically, if we start from a set of token representations, which can be represented by a matrix X, I, J, where I is going to range over tokens in the text, and J is going to range over embedding space. Then we're going to construct three kinds of new representations called Q, K, and V. And each one is given by a matrix product of a weight matrix, W, Q, K, or V, and our input representations X. So we construct three kinds of new representations based on X, Q, K, and V, and then we do this. So we take products, inner products of Q and K, and then those are going to give us the coefficients that we just talked about. So inner product of Qi, or Qi and Kj can give us the coefficients that we need for each j that we will use to replace token I. So it's some notion of how similar tokens I and j should be in the representation space. And then V is just a transformation of X that we will then use to form a basis of our new X. So if we just take this formula here, it has softmax, which we will use to convert the inner products to normalized probability distribution. So if you remember how softmax works, if you pass a vector to softmax, it's going to return another vector whose entries add up to 1. It's a soft version of taking the maximum. Okay, so if I did write out what is inside the softmax in terms of W, WQ, WK, and X, you would see that this product WQ times WK plays an important role. It basically defines a sort of a metric in the embedding space. And what we're doing here is we will be taking various low rank approximations of this metric. So another thing here is that the operations here we may want to do a number of times because we may want to capture a number of different concepts in the text.
So I'll ask you a question about the metric. So metric supposedly measures distances, right, in the embedding space. Is that the idea? Now, do you know if it satisfies triangle inequality or?
Well, this is not
It's not.
exactly a metric.
It's not a metric. Okay. Some. Okay. Is it
It's
like positive?
I don't think there are any constraints basically, other than being low rank,
I see.
because
Well, there
it
gotta be
it's
some constraints, but okay.
because
Fine.
WQ and WK can be pretty much anything, so their product can be also pretty much anything as long as it has the appropriate rank.
Okay. Fine.
So in what sense is it metric? If you write out what Q K transpose is, it's going to be something like X transposed sandwiched, and then sandwiched in it is going to be WQ WK. So they're basically like coefficients. So you can replace it with G, and then this will be something like XI, X transpose J, GIJ. So that's kind of vaguely reminiscent of what a metric could be, or GIJ or AIJ would be this product of WQ and WK.
Well, WQ and WK kind of linear transformations, but then you still find an inner product there, no? They're like linear transformation of X vector.
Yeah, for sure.
But then you
Q
still
and
find
K
an
are
inner product. And so presumably, if it's in a product with itself, it should be positive. And okay, fine.
mm-hmm. Yeah, so basically, yeah, it's reminiscent of metric, but there are no constraints on it as far as I can see.
Sure.
But maybe there should be. That's
Right, exactly.
Discussion.
Mm-hmm.
Right. Because we may want to capture like a number of different notions of which tokens are similar to each other. So, one of them could be, I don't know, like emotion, another one could be color, various kinds of concept spaces we want to capture. So because of that, we take this operation a number of times. So we have a number of heads. Each head here will have its own set of WQ, WK, and WV matrices. And each head will generally produce an output that is lower dimensional. So if our original dimensionality for embedding space was D, and we have H heads, then generally each head will produce an output that's D over H dimensional, which we call YI here. And then we're going to concatenate all of the outputs of different heads. There are H of them, H D over H dimensional vectors, and they're going to produce something that has the original dimensionality. So those are the basics of multi-head attention. I would just say just one more thing here, that after we do all of this, commonly we would also apply another linear transformation to this concatenated vector, which is sometimes called WP. And the point of this is kind of that, we did a number of transformations corresponding to different heads, and they rearranged components of the original vector to something that's organized quite differently. And then this WP, the goal could be that WP could give us a vector that's organized similarly to our initial vector. So you can see maybe a bit more of that on the next slide, but just want to mention that. So here, we can see the novelty of this paper. So on the left is sort of the original transformer architecture. So this is something called transformer block, which is a sequence of transformations, which then larger models just repeat over and over and over again. So a language model may have many transformer blocks. Each of the transformer blocks would have different set of trainable weights. So on the left is the sort of original transformer block with one small novelty. First thing I want to point out there is well, first of all, how do we read this diagram? So So you may notice that there are little circles with crosses and circles with pluses. So cross just means matrix multiplication, and plus means a weighted sum. Sum or could be a weighted sum. So so first thing I want to point out here is, as you can see on the left, so we have this transformation that's repeated h times. That's multi-head attention. And you can see that following it, we have this proj element. So that would be the WP. They're basically just a linear transformation on the output of everything.
But hold on, is it a projection operator? Does it reduce the dimensionality or just rotates and stretches, squeezes?
So in general, you could have attention, multi-head attention that could produce a different dimensionality than the original dimensionality, and then this could bring it back down to original dimensionality. So I think
so you first go to a larger dimensionality and then you project it back to a smaller one.
Yeah, that is possible.
Okay.
I do think that in their paper it keeps dimensionality fixed.
But why is proj means stands for projection or
stands for projection? Yeah, but it could it could keep the same dimensionality. Yeah, it's a linear
but not the other way around, right? So they don't want it to have a small dimensionality first and then.
I don't think so. Yeah.
Okay.
Okay, so that was proj, and then a couple of other things. So you may notice those norm elements. So norm is a layer normalization. What does layer normalization do? So layer normalization is somewhat similar to batch normalization that you may be familiar with, but it is different in the sense that it doesn't normalize things across batches, it normalizes things across the embedding space. So if we take, so as input to this model, we may have number of token embeddings, or as input to this block, or the model, we may have a number of token embeddings, and then norm will normalize embedding of each token, will first normalize the embedding of each token such that the mean of the features is 0 and standard deviation is 1 or something like that. So it's a linear transformation. We could do that. And additionally, we may allow trainable means and sigmas. So we may normalize such that the mean is mu and standard deviation is sigma. So do a linear transformation such that mean is mu and standard deviation is sigma for each token embedding. And then mu and sigma could be trainable. So so you may see that the title of the left transformer block is pre-LN. So that means that the layer normalization is applied before attention rather than immediately after, I guess. So so it is a version of the original transformer where layer normalization is applied before attention. And then we're almost there. You can also see the on the left diagram, you see the MLP in and MLP out. So MLP stands for multi-layer perceptron.
So Stefan, if you point with your arrow, we will see what you.
Oh, okay.
Oh, okay. Perfect.
Okay, good. Yeah. So MLP in and MLP out. So MLP just stands for multi-layer perceptron, which is basically a fully connected layer of a neural network, or equivalently just matrix multiplication by weight matrix of a certain dimensionality. So so you can see here at the end, there's basically one linear transformation, MLP in, followed by non-lin, which is the non-linearity, followed by MLP out. So this is basically just a simple fully connected neural network with 2 layers. And one final thing, you may have noticed those those skip connections. So so this just means that we're going to add the original input to the output of this whole multi-head attention plus projection operation. And similarly here, the output of that then goes straight to the end, and it's added to the result of performing those multi-layer perceptron operations. So yeah, and any questions there?
So in a sense, the role of this projection is to really keep yourself into the original space, and then this whole transformer block in the bottom just makes an adjustment to what the vector should be in the embedding space, right?
I think so. Yeah.
And the same for this follow-up fully connected layers, right?
Mm-hmm.
So you want to still that to be kind of maybe a small perturbation to what
we had before. Exactly. Right. Yeah, so I guess the idea behind those skip connections or residual connections is that basically you want to learn some sort of perturbation to the original input. And it's easier to learn a function that's close to 0 than a function that's close to 1. So without those connections, we would need to learn a function that's close to 1. With connections, those ways just need to learn a function that's close to 0. So right, so that is the sort of original transformer block that is widely used basically with small or non-existent changes in most language models. Okay, and then on the right we have two novel models. So one of them is called parallel, and that came from this paper from 2021 by Wang and Komatsuzaki. And the other transformer block is denoted hours, and that is the contribution of this paper which we're talking about today. So the main novelty in parallel block is that we can perform those multi-layer perceptron transformations, or basically fully connected neural network transformations. We can perform them in parallel with attention rather than perform them after the attention.
And that's okay if perturbation is small. It's like
exactly.
I see. And that there's no difference if it's small.
Yeah, I think that's exactly the idea. If the perturbation is small, then there is no difference. So that is the main novelty of that transformer block. And then in the transformer block here on the top right, there are a couple of novelties with respect to parallel. So of course, one novelty with respect to pre-LN is that we are using this parallel architecture. Okay, and then novelties with respect to parallel, I think there's 3 or 4 of them. So first of all, the thing that's most glaring here is that they got rid of V. So V is gone and is basically just replaced by an identity function. Okay. Then they got rid of this big skip connection here that hopefully you can see. I'm tracing it with my cursor. So that is gone in this model. Okay. Next thing is they got rid of the normalization. So this normalization here is absent in the model on the top. And and yeah, of course, another thing which is also kind of glaring is that they got rid of this proj operation. So I think those would be the 4 novelties. So they got rid of proj and V. They got rid of norm, and they got rid of this skip connection here.
But then in what sense now it's a small perturbation? Because now we want to make sure that this overall transformation block is close to identity. Before it was enforced by this skip connection plus small adjustments, but here I don't see any constraints.
Yeah, so that's a great question, and I think I'm lying a little bit when I say that they remove the skip connection, because they do replace it with something that's very similar.
I see. Okay.
Right. Okay. So now let's just go through those things in a bit more detail. So yeah, regarding that question, the question that we just had. So they do technically get rid of the skip connection, but then they replace it with something pretty similar. So what they're replacing it with is this notion of shaped attention. So first of all, let me define what I mean by this A of X. So if you remember, let's just go back here. So if you remember the attention, this formula for yi. So we take inner products of Q and K in order to decide which tokens should have similar representations. And then we make them similar by averaging with respect to those coefficients, by averaging V with respect to those coefficients. Okay, so basically what they're going to call A of X is this product of, is this softmax of Q times K. So everything here except V, that's what they call A of X. So, and as you can see here, this is basically this should be product of Q and K. Where Q is just defined by WQX and K is just defined by WKX. And then there's also like one more element which I didn't mention before, but that's masking. So we do masking in transformers in order to make sure that we follow causality, basically. So as we go along the text in common types of models, we want to predict the next token at each position. But we often want to predict the next token only based on the tokens that came before, not looking at that token and the future. So that's what mask makes sure of here. So mask M will make sure that attention only looks at things that are in the past and not things that are in the future. In this kind of model, at least, this kind of autoregressive model that's predicting the next token. Okay, so that's what we have here. It's just a product of Q and K, basically. And now what shaped attention does is it adds two modifications to this. So it replaces A of X with this combination here, so that we still have beta times A of X, where beta is some trainable coefficient, but we're also adding identity matrix, IT, and we're also getting this constant matrix, not non-trainable matrix C. So what is the idea here? So IT is kind of like a skip connection, but inside of this attention itself. So like rather than having this skip connection that's kind of outside of the multi-head attention, now we have something like skip connection inside.
But that's the same thing. You're still,
getting
the same information.
Yeah, for sure. It's the same thing. So, all right. So that's it. That's basic skip connection. And now, what is the point of gamma C? So this is added, in this second paper by Nossi et al. And it's basically in order to reduce oversmoothing. So oversmoothing is a phenomenon that can happen in deep transformers, especially after some changes were made, like if those multi-layer perceptrons were removed, or maybe if the skip connection was removed. So oversmoothing would mean that if you go like really deep into the transformer, then all the tokens would end up having roughly the same representations. So if you look at what attention is doing in those cases, it would be kind of like equally attentive throughout the text. And in this study from 2023, they found that removing this constant can help reduce oversmoothing. So what is CC is non-trainable, and it's defined as or set to the value of A of X when the product here, this complicated inner product of Q and K, when that is identically 0. So then it's just softmax of M. If M was if there was no masking, so M was absent, then or absentory identity, what would be, then C would be literally constant. With non-trivial values of M, it's not literally constant, but it's a matrix that we compute, and then it's not trainable. Okay, so they replace A of X with this combination here, where alpha, beta, and gamma are trainable parameters.
Stefan, I'm still confused about C, because that seems to be like if you apply this transformation many times, then this C will be just adding up. Of course, there's maybe in nonlinearities that will act non-trivially on C, but at least in the perturbative limit, it will be just, shifting things in a certain direction. But so I'm not sure I completely understand the meaning of C.
Yeah, that's fair. I'm not sure I completely understand myself too.
Yeah, so, but you're saying that just, and also you have to initialize it somehow, right? It's not something that you learn, is it?
No, it's fixed.
Okay, well then.
Yes. So yeah. So
I would think like in this, if the idea is after each block you want to roughly remain in the same embedding space, there has to be kind of three terms: identity, right? Because you're close to where you are. You want to have some drift in the direction where you go, and so you have this A matrix. You may add maybe some stochasticity, so that it doesn't get stuck in the local minima. But I don't know if they've been adding that or not, or maybe it's intrinsically in A. But C is seems to be a constant drift, and then if you apply this many times, then this matrix will dominate over identity and anything else, and so identity will be irrelevant, right? So this will be the most biggest contribution will be just coming from C. But maybe there's something I don't understand about this matrix. At least naively, it seems to be pushing things in the unknown direction when you shouldn't be. But maybe because of narratives, it has
just thinking off the top of my head, if the activation dynamics was such that it would produce something like A of X equals gamma C, or gamma C times the number of layers.
Yeah.
If you produce something like that in the limit, then we're subtracting that.
Right. So that's right. So maybe there is in AX there is a correct dynamics, and then there is a useful drift that's an artifact, and then you identify this useful drift, bring things back to where they were. But then C would have to be learnable, trainable somehow. But you're saying that you start with, so if it's not trainable, then I don't understand where it comes from. But it's okay.
Yeah, we can.
Still, the idea, I think, is very interesting.
Yeah, so you can produce a study where they basically consider limits of transformers that's so if you have two parameters, so width and also D of embedding space, something like that. So they consider large D and large N, but they keep N over D fixed. And then in that limit, I think they show that this works well. So yeah, that's not super illuminating, but yeah, maybe we can come back to that. Yeah. So yeah. So okay. So that's one thing. So just empirically, it works. So that's just the shape attention. And then another thing is, and now, so this shaped attention basically is going to replace the skip connection. The first term, at least, the alpha IT is pretty similar. Okay, and then the next thing, the second bullet point goes into removal of WV and WP. And WP, if you remember this proj element here, that's WP. Okay, so in order to sort of see that those can be removed, so they do the following. So they reparameterize W's in this way. So they replace WV, which is trainable, by this combination of WV initial, which is non-trainable, and delta V, which will be trainable. Similarly for WP, there is WP initial and delta W. And so WV initial and WP initial are going to be, or they fix them to random orthogonal matrices. And also they
are they making an assumption that this delta W will be smaller than because if they're of the same size, then there is no reason.
Right. So alpha and beta are trainable also. And the next plot, so I think that here they fix alphas to 1. And then they train and look at what betas are. Or sorry, they train 4 different values of. All right, so in that case they will not be trainable, but I think that here they train for different values of beta V.
But do they have like a plot of the matrix norm of the initial W's and this delta W's, like to see whether there is difference in the matrix norm?
I don't think so.
Okay. But do you think we should be thinking about them as perturbations or not necessarily?
Well, okay, so okay.
It's difficult to answer.
They actually kind of have something like that. Sorry, so here they also train alphas and betas. And what they find is that as the training is progressing, betas are becoming small relative to alpha.
Oh,
so that is kind of like what.
Okay, so the system wants to see those terms as perturbations. You're saying?
Yes.
Okay.
And also they do more than that. They completely kill them.
They kill it.
Like yeah. So if we kill betas, then WV and WP will be orthogonal. And if you look at what they do, so like first,
sorry, orthogonal but not trainable, or trainable as well. Are these initial ones?
So they're going to be completely gone, not just non-trainable, but replaced with identity.
Deltas gone or initial gone?
Yeah, so they're going to replace WV and WP by identity matrix, basically. And this was like an argument for how they can get there.
Oh, I see.
So if WV and WP are orthogonal, then because in a sense, the product of WV and WP is the only thing that matters. And they're orthogonal, then they can just kill them.
Orthogonal in the sense of the matrix norm, I guess, right? Orthogonal in sense of...
No, I think just in the sense of matrix multiplication.
Are you saying that the product of matrices will be 0? Like close to 0?
Oh, well, okay, good point. I think the product will just be identity.
I mean, it could be, but I would be surprised.
I'm guessing
W's are still not a square matrices; they're rectangular matrices. So
yeah,
if you are to multiply them, you're probably going to do it with the transpose. But maybe maybe you're right. Maybe
no, I think you're making a good point, because it's kind of unclear what it means for 2 matrices to be orthogonal. Right? It's not a standard term even. It is for 1 matrix, but not for 2 matrices.
Yes.
I'm not completely sure, but just
I would think it is, taking matrix with its transpose, right? So you multiply it, and then you take a trace, and that's the guy that is 0. So and that is equivalent.
Yeah, that is.
So that's kind of my best guess what it would mean.
Yeah, that is a good definition, right? So that would amount to like basically flattening the matrices, and then as vectors they're orthogonal.
Exactly.
But I'm guessing, based on what this model does, that they mean something else. I'm guessing that they just mean that their product is identity matrix. Why? Because if you see here, we apply V as a matrix product, and then we apply P as a matrix product. So they're basically just 2 consecutive matrix products, and if their product is equal to identity, then both V and P can just be killed.
I see.
Yeah, the subtlety here, I guess, is that their dimensions don't actually match. So V is projective. So V is taking us from D to D over H, where H is the number of heads. But P is actually just, in a sense, rotation, just taking us from D to D. But I would guess that what they do is they pad V with zeros, and then those are orthogonal. I'm guessing that that's what they do. Okay, so this is basically their argument for why it makes sense that that we can remove V and P. So if we do this kind of parameterization, and then we look at what is beta versus alpha, basically their point is that beta wants to be small compared to alpha. And you can see here, if we vary beta, then loss will be smallest when beta is 0. And similarly here, if you let beta be trainable, then beta versus over alpha wants to be 0, both V and P. And then
also, it may be in the sense that they're orthogonal, like orthogonal matrix, and then one is orthogonal matrix, and the other one is the inverse of orthogonal matrix. If that's the case, of course, their product would just be identity. Maybe that's okay, but I understand. So the point is to show that it is the direction of their product.
Right. That's a good point, because they could just be like two orthogonal, like WV could be orthogonal and WP could be orthogonal.
Right. And the other thing, if they are random orthogonal matrices, and if they are random orthogonal matrix, which is what's written here, and those random orthogonal matrices in a very large dimensional space, right? So then I don't think that they would one be the inverse of the other, right? So it'll be just one rotates in one direction, the other one rotates in the other direction. So the overall is again get an orthogonal matrix as their product, and so there's no sense in which it's small. Now there is a sense in which this rotation is useless, basically, because there's no stretching or squeezing, there's no projection. It's just redefining. It's a symmetry, so you can always get rid of it. Maybe that's
okay. That is a good point. That is a good point. They don't. It doesn't have to be the case that their product is identity, but it could be the case that they're both useless.
Right. Exactly.
Right. Yeah. Okay. So I think that is right, because that's what it means for matrix to be orthogonal. It just means that matrix C is orthogonal.
Yeah.
Okay. Anyways, so this is basically just to argue that we can remove
betas, right?
Yeah, we can remove betas, exactly. So we can, eventually we can remove. Well, because also another thing is that if I guess I'm just repeating what we just said, but they're both going to be, if they're both orthogonal, then it's their combination is just an orthogonal matrix which does nothing. So
it does rotation, but it doesn't do anything useful for learning.
Exactly. Yeah, it doesn't go
into redefines what you call XYZ in this embedding space. In a way, you there is the symmetry. You can always
you can always rotate.
Nothing going to change for that.
Right. So so this is just to argue that we can remove betas, and then what follows from there is that we can set WP and WV to identity, and they will do this and then show that results are good. But then one final thing is just removing or parallelizing the transformer block. So this is probably was kind of obvious, from that diagram I've shown. But basically, because they're going to parallelize the attention part and this fully connected or multi-layer perceptron part, then this is going to be the formula that relates input X in to the output of this model. So, and just something to note here is that this came originally from this formula came from this paper where they parallelized the attention block. And in this paper, they also had the first term, which was essentially a skip connection. Okay, then in the paper that we're talking about today, they got rid of that. And they got rid of that, and they also set the coefficient or like, I guess the initial value of the coefficient for the multi-layer perceptron to be low relative to attention. So maybe that can, I mean, these are just initial values, but maybe that can also be taught, or like the idea is that they want to think of MLP as a perturbation on top of attention. Okay, and then now I'm just going to show like some of the results. So SASP, this is how they call their model. Basically what this shows is that performs similarly, I think a bit better to pre-LN, which was the original transformer. I think here pre-LN is the purple line, and I guess you can see that that SASP is performing a bit better. But also the point is that even if it was performing exactly the same, it has fewer parameters because we got rid of a bunch of stuff, and it is faster to train. And the point here is also to show, I guess you can see two kinds of lines for each model. So one is depth equals 18. That's the connected line. You can see here. So depth would be how many times we repeat the transformer block. So repeat the whole thing 18 versus 72 times in dotted line. And I think the point here is that, for example, for this V-skipping model, which got rid of one of the residual connections but didn't make the other corrections that they made, it actually gets worse as we increase the depth. But for their model, you can see improvements as we scale from 18 to 72 for all of them. Okay, and just some more experiments. Point here was that, while they originally studied this on so-called autoregressive models, which are just trying to predict the next token in the text, they also like apply this same kind of transformer block in a different kind of model, in a bidirectional model. So bidirectional models, I don't know if people are familiar with, for example, BERT as an example of a bidirectional model, which was very popular in natural language processing for a while. So the idea of bidirectional models is that we do not want to necessarily just restrict ourselves to looking at words that came before or tokens that came before and trying to predict the next token. We also want to potentially look at tokens that come before, tokens that come after, and then try to predict tokens in between. So the way masking works in these models is they just select some subsets of tokens and then mask them and then try to predict those. While masking in autoregressive models, we're always masking everything that's to the future.
So they're just replacing the matrix M that you had before.
Exactly. Just replacing the matrix M. Yeah. So yeah, and like what it shows is that the same kind of transformer block also performs well in this kind of model. Okay, and just some benchmarks here. Could be interesting to see how many parameters they had. I think in the version with 18 transformer blocks, they had around 100 million. With 72 blocks, they had 4 times more. Actually, 4 times more parameters. Yeah, this is just to show that compared to pre-LN, which was the original transformer block, on some benchmarks, so performance is similar, but you can see that there is roughly 16% fewer parameters, and speed is 16% faster. So similar for performance, but fewer parameters and faster. And yeah, so basically just to repeat that, they managed to they managed to come up with a similarly performing model with fewer parameters that trains faster, and also like with significantly simplified architecture of the transformer block. And one caveat here is that the model sizes trained were between 100 and 300 million or so parameters, and it still remains to be seen if this will work when this model scales to the size of LLMs or large language models, which can be several hundred billion parameters. And that is all I wanted to say.
Thank you. So I have one question about the last slide, maybe a quick question. So yeah, I understand that they were not able to test it with 100 billion parameters, but have they looked to see how those results scale in the range where they can test things, right, around 100 to 300 millions?
Mm-hmm.
So maybe like, you know, there's 15% starts decreasing within the range that they can analyze, or it starts growing. So that's the first question. Have they looked at how these things scale with the size of the number of trainable parameters?
Yeah, so I guess the question is
actually in both directions, right? So 15% is what they got for 100 millions, but you know, if they had 1 million, or if you had 300 million, would it still be 15%, or would it grow in one direction?
I think 15% is with respect to, like, if you compare two transformer block architectures.
Right. So that's what I want to see, how does this 50% evolve as you increase the number of training?
So I'm not sure, but I think that should scale linearly, because we are just each transformer block is smaller.
Well, if it's linear, then it's a good argument suggesting that in which way a good argument suggesting that nothing strange should happen for 100 billion, and unless there are some
so in the sense that the number of parameters will be better, yes, but I think the other question is, like, will the model like start to perform worse at some point? Which is possible, and I guess the comparison.
That's right. I'm saying. So there may be something like that doesn't appear for 100 million, some important feature of the regular transformers, but big. And then I'm saying that you can identify it early without having to run for 100 billion. Just look at the tendency of how that changes. Okay.
I guess they have this comparison between dotted line and full line. So it does perform.
Oh yeah, exactly. That's
perform better at deeper.
That's exactly my question. Okay, good. Perfect. Other questions? Comments? All right. Well, thanks everyone for coming. We'll hopefully have a volunteer for next week to present a paper. And if you found an interesting paper, just post it in the Telegram chat, and we'll go with it. Thank you, Stefan. Thank you so much. That was fun.
Thank you, everyone.
Thanks, Stefan.
Thank you.